Our natural satellite represents Earth's only cosmic companion and stands as the closest celestial body to us. Most likely, the Moon's formation occurred as a result of a collision between our planet and a cosmic body of Martian proportions. This cosmic catastrophe happened several billion years ago. The impact melted Earth's surface and sent a massive fragment of matter into near-Earth space, which subsequently cooled and formed a spherical body. Today, this crater-covered sphere orbits around our world, triggering oceanic tidal phenomena. The Moon's dimensions comprise approximately 1/4 of Earth's diameter. Due to this, it holds fifth position among the largest natural satellites in our stellar system. Lunar cycles include various stages: the new phase, full, crescent, as well as first and final quarters. Regardless of the current stage, our cosmic neighbor is easily distinguishable among other astronomical objects in the nocturnal and sometimes even daytime celestial sphere. Imagine this situation. You awaken in the middle of the night and notice that the Moon appears unusual. It seems brighter and larger. However, in a drowsy state, such differences aren't so obvious. You return to bed, not suspecting that Mercury has taken the Moon's place in the heavens. Mercury's landscape, the planet closest to our star, bears resemblance to lunar topography. Its surface is riddled with traces of meteorite impacts. Mercury's dimensional characteristics don't even reach half of Earth's parameters. However, it exceeds the Moon in size, which would cause its more substantial impact on our planet. Nighttime would become brighter. Tidal effects would intensify along with ebb processes. The duration of the lunar month, the time period during which our satellite, or more precisely, Mercury in this case, would complete a full cycle of phases, would shorten by 14 hours. Nevertheless, such a replacement wouldn't radically alter planetary conditions. What about Venus? Imagine that instead of the familiar satellite, the sky would be adorned by the third most intensely glowing natural object after our star and the Moon. Venus is often called Earth's sister due to practically identical mass and size indicators. In Earth's sky, Venus would appear as massive as our planet appeared to Apollo mission astronauts observing it from the lunar surface. The morning star would emit significantly more intense light than the Moon. First of all, the planet can reflect solar radiation in 6-fold volume. Additionally, it would occupy at least 16 times more space in the celestial expanse. For this reason, Earth's nights would acquire brightness characteristic of early twilight hours. When observing Venus, one could distinguish blurred spiral structures on its yellowish cream cloud surface. Venus wouldn't become Earth's satellite. More likely, both planets would rotate around their common center of gravity, and such an orbital configuration would feature quite unusual characteristics. If Venus moved at lunar velocity, the planetary bodies would inevitably collide in the foreseeable future. Well, shall we continue our investigation? If Mars replaced the Moon, it would be impossible not to notice due to its reddish disk and planetary dimensions twice exceeding lunar parameters. Optical instruments wouldn't be required to observe the unusual coloration and dark regions covering the planetary surface. And even without paying attention to the red planet, you would certainly feel unfavorable changes. Mars is half Earth's size, but exceeds the Moon many times over. Replacing a small cosmic body with a larger one would lead to the destruction of delicate equilibrium. Under unfortunate circumstances, if Mars taking the Moon's place caught you on the seashore, immediate evacuation would be required. Planetary influence would provoke the formation of most powerful wave formations that, like colossal tsunamis, would crash upon the coastline. Mars would reflect solar rays more intensely than the Moon, making nights brighter. Earth's landscapes would acquire an ominous reddish tonality. However, telescopic observations would allow admiring Olympus, the highest peak in the entire solar system. Mars isn't massive enough for radical alteration of Earth's orbit. However, over time, both planets would inevitably begin orbital movement relative to each other, forming a binary planetary configuration. And since Mars would appear so close, interplanetary expeditions would become achievable reality. It's time for more grandiose contemplations. If Jupiter replaced the Moon, Earth would lose its status as an independent planet. It would transform into a satellite of the largest world in our stellar system. However, positive aspects exist. People would gain the opportunity to contemplate skies of stunning beauty. Jupiter immeasurably exceeds the Moon, and the gigantic striped sphere would stretch across the entire visible horizon. The opportunity would arise to admire yellow, brown, red, and white cloud formations floating in Jupiter's atmosphere. If there were enough time for this, unfortunately, the gravitational impact of the gaseous giant would immediately cause seismic upheavals, volcanic eruptions, and tsunamis. Earth's crust and mantle would begin being pulled toward Jupiter, leading to planetary destruction. The planet would be compressed and stretched in various directions by 90 meters. Unfortunately, Earth's velocity comprises only 1/10 of what's necessary to maintain Jupiterian orbit. Precisely for this reason, in less than 24 hours our world would collide with the gaseous colossus. But let's turn away from sad scenarios. Moon's replacement by Saturn would present an unforgettable spectacle. The planet exceeds our satellite by more than 35 times. The golden sphere would occupy 18 angular degrees of the celestial vault, while the renowned ring structures would stretch from one horizon to the opposite. Earth would be positioned somewhat farther from the gaseous giant than its moon mass. Since Saturn is significantly more powerful than our planet, Earth would become its satellite. Unfortunately, Earth's orbital velocity would prove insufficient, and within several days we would collide with Saturn. However, before reaching the planetary atmosphere, one would have to pass through its delightful ring systems. They are formed from fragments of comets, asteroids, and destroyed satellites. Such a route would present significant complications. One shouldn't forget that Earth would need to navigate around Saturn's satellites, numbering 53. But suppose the collision didn't occur and Earth became the 54th satellite. Then the gravitational impact of the gaseous giant would provoke the most powerful tectonic shifts across the entire terrestrial globe. The planetary crust would tear into fragments, ultimately leading to complete annihilation. This is also not a very optimistic outcome. Uranus and Neptune represent ice giants. They have approximately equal sizes. They exceed Earth but are inferior to Saturn and Jupiter. Both planets are covered with ice masses and possess an attractive green-grey hue. If either replaced the Moon, consequences would be identical. Therefore, let's make a random selection. Excellent. Let's examine what would happen if Neptune appeared in the heavens one day. Neptune exceeds the Moon 14 times over. The planet would resemble a huge bright blue balloon not only during daytime, but also at night. It would seem that Neptune is 15 times larger than the Sun, and solar eclipses would be regularly observed. After the Sun's concealment behind Neptune, our planet would plunge into absolute darkness for more than an hour and a half. Neptune's mass exceeds Earth's 17 times over, and its gravitational attraction is significantly stronger. Consequently, our planet would transform into a satellite. Exactly so, again, it would orbit around Neptune at somewhat greater distance than its largest satellite Triton. Incidentally, under such conditions Earth would risk eventually colliding with this cosmic body. But let's assume a favorable scenario where encounters with Neptune's satellites didn't occur. Nevertheless, there would be enough problems without this. Earth's waves would become 1,000 times more powerful than lunar ones. Neptune's gravitational impact wouldn't tear Earth apart but would heat our planet. Seismic activity would gradually intensify, provoking earthquakes and volcanic eruptions. Internet connections would likely cease functioning. Imagine mentally two parallel horizontal lines. Now connect them at arbitrary points using two different methods. A perpendicular line directed strictly upward from the lower to the upper, and an inclined line, which is shorter. Naturally, the perpendicular one. This is the shortest way to connect the upper and lower lines. And this is the fundamental answer to our question. It's more optimal and faster to reach orbit along a straight trajectory. The lower line symbolizes Earth's surface. Our planet represents a complex composition of diverse substances united into an impressive mass, approximately 6 sextillion tons. This is equivalent to 6,000 billion billions. Simply put, an enormous number of zeros. Actually, all this mass functions as a gigantic magnet that, among other things, provides Earth with maintenance of what everyone knows, the atmosphere. The upper line denotes the atmospheric boundary. Everything located higher constitutes planetary orbit and open cosmic space. However, the atmosphere itself is also filled with matter. This is a combination of gases possessing their own density. During shuttle launch, the entire gas mass continuously presses on the apparatus, creates friction, and significantly slows movement. Passage through vacuum resembles cutting through air, while movement through atmosphere is more like attempting to break through a gelatinous substance, grape or strawberry flavored. Considerable energy and power are required to overcome this medium, while simultaneously experiencing the attraction of a colossal gravitational magnet called Earth. Aircraft don't suffer as much from atmospheric passage since they use its density for terrestrial separation and altitude maintenance. Two components assist them: engine thrust and wing configuration. Aircraft wings force air to divide into two streams. Naturally, the streams strive to reunite behind the wings, but their shape compels the upper stream to move faster. The more intensive the air movement, the more density is lost. This means the stream under the wing is denser than the upper one. Gradual aircraft lift is created. Essentially, wings provide aerial gliding for the aircraft. Naturally, this would be impossible without enormous force propelling the aircraft forward. This is precisely why thrust is necessary. For terrestrial separation, an aircraft requires development of tremendous speed. The necessary speed varies significantly depending on aircraft type: 96.5 km per hour for light aircraft and approximately 241 km per hour for passenger liners. For takeoff and ascent to 3 km altitude, a Boeing 747 needs slightly less than 3 tons of fuel. Perhaps this sounds impressive, but let's consider the Space Shuttle. Initially compact, miniature, and short wings attract attention, which would prove ineffective during horizontal takeoff. On the opposite side, more massive wings would become useless in cosmic vacuum. Additionally, they would be difficult to manufacture sufficiently strong for launch loads. Small shuttle wings serve a single purpose: safe landing, allowing apparatus reuse in subsequent missions. Their dimensions should suffice exclusively to prevent uncontrolled shuttle rotation during atmospheric descent and deliver it to Earth, since engines aren't activated during landing. Shuttle engines differ fundamentally from aircraft engines. Aircraft engines require atmospheric air for functioning. Obviously, shuttle engines don't need it, since discovering atmospheric air in cosmic conditions is problematic. Therefore, rocket engines are used in shuttles. To demonstrate the meaning of the term rocket and the principle of functioning, simply inflate a balloon and release it. It will spin until completely empty, constantly moving in the direction opposite to the exiting air. For takeoff, a rocket engine must generate sufficient thrust and burn the necessary fuel quantity. In reality, the space shuttle during takeoff requires so much fuel to achieve needed thrust that it couldn't manage exclusively with 3 engines. It needs 2 additional solid fuel rocket boosters and a separate enormous fuel reservoir that's jettisoned at the final launch stage. Moreover, the shuttle can reach orbit only with sufficient power. The shuttle's power with 3 engines and 2 boosters comprises approximately 3.5 million kilograms of thrust. To provide such a powerful impulse, the external tank contains about 725,000 kilograms of rocket fuel. And for flight control, these 3 engines must possess astoundingly complex construction. But did the possibility exist for orbital shuttle launch with its modification for atmospheric use like aircraft? Unfortunately, the answer is negative. Even more fuel would be required to maintain necessary speed throughout the diagonal launch trajectory. The point is that even when an aircraft reaches the upper atmospheric layer, Earth still won't release it. For atmospheric exit, any object rising from Earth must possess sufficient speed to cross the point of so-called escape velocity. It's necessary to overcome planetary gravitational attraction and put the object into orbit. Our planet's orbital velocity comprises 28,000 kilometers per hour. Obviously, this significantly exceeds sound velocity, many times higher than a passenger liner's cruising speed. Try to imagine an aircraft moving at such speed. How much fuel would it require? Additionally, it must possess sufficient strength not to break into fragments. Cost and technological complexity would prove simply unrealistic. The probability of shuttle obsolescence became the reason for scientists and engineers' attempts to discover better solutions for orbital exit and extra-atmospheric travel. One such concept suggests that in the future people will ascend to space via an enormous space elevator. The space elevator represents a concept of a gigantic tower extending to an orbital satellite that moves synchronously with Earth's circular rotation. The tower's height should comprise about 35,400 kilometers, and it should be manufactured from incredibly strong material, carbon nanotubes. The platform inside the tower is planned to be set in motion via electromagnetic thrust mechanisms. Travel from Earth to satellite would take only 5 hours. Such a megastructure would provide faster and safer space transportation. However, carbon nanotubes proved insufficiently strong for constructing such a gigantic tower, so the search for ideal materials still continues. Another project using a similar approach is called a space tram. The construction necessary for project launch isn't so large, but still impressive. This is a vertical vacuum tunnel that will push a shuttle levitating on magnetic thrust. Air won't be able to slow it down, while pushing through the tunnel, and acceleration will be provided by electromagnetic force until the shuttle breaks into the sky at speed approaching escape velocity. Such a shuttle would have less mass since it wouldn't need to transport large quantities of fuel. However, it's still not mentioned how a human would endure such acceleration. After all, upon arrival the crew might turn into a flat mass. If such concepts seem strange to you, and they really are, prepare for the final idea. Perhaps people will use aircraft for orbital ascent. No, this isn't deception. An aircraft by itself won't be able to reach space, but can serve as a launch platform. Even better, for this purpose, a special aircraft will be created with wingspan of practically 122 meters and capability of ascending to heights exceeding 10 kilometers. A small shuttle launched from such an aircraft won't have to overcome a significant atmospheric layer. It will be easier for it to overcome Earth's gravitational attraction. Richard Branson is already working on this solution within the Virgin Galactic program to deliver tourists to the space boundary.